In this section, we will be learning about all the functionalities and options that we have in the render setup window. And in this lesson particularly, we'll be discussing color mapping. In the render setup window and under V-Ray tab, you can find the color mapping rollout. And probably we should have discussed color mapping in the global illumination or image sampling section of the course, but I've decided to unify all of the render setup settings in one section. So what is color mapping? Basically, color mapping is an internal process that maps the colors rendered by the render engine to a range that is visible by human eyes and also in the monitor. It basically maps the low and high color values to a range that is visible and usable for us. In most render engines, this is hard-coded in the engine and we as user cannot adjust it. But in V-Ray, we can actually control all the aspects of the color mapping process in the color mapping rollout. So let's see what do we have here. For now, let's set the interface to expert so we can see all the parameters and options. First, in the type dropdown, we can control the overall color mapping mode that will be used. We have linear multiply, exponential, HSV exponential, intensity exponential, gamma correction, intensity gamma, and rain hard. Let's start from linear multiply and see how it performs the color mapping as we take a look at the render performed with this color mapping. Linear multiply simply multiplies the final image colors based on their brightness without applying any other changes. And as you can see from the render, this color mapping clamps bright colors to white and causes the bright parts of the image to look burnt out or overexposed. So in this mode, each pixel is gonna be multiplied by its brightness, and that's why we get a very vivid and bright image. However, because of this linear nature, we get overexposed and extremely bright and burnt out areas in the render. Next, we have exponential color mapping. Exponential saturates the colors based on their brightness, and this can be useful in preventing burnouts in very bright areas. But you can see the final image looks desaturated and less vivid compared to the linear multiply color mapping. But we have no burnt out and overexposed parts in the image, which is great. Exponential color mapping is especially useful in interior visualizations. HSV exponential is similar to exponential, but preserves the color hue and saturation instead of washing out the color towards the white. And it tries to solve the dullness and desaturated colors produced in the exponential color mapping, but trying to preserve the color saturation in bright areas that in real world tend to get closer to a white color doesn't produce a pleasant image, honestly. We have intensity exponential, which is similar to exponential but preserves the ratio of the RGB color components and will only affect the intensity of the colors. Gamma correction and intensity gamma are here for legacy purposes, for when there wasn't a gamma correction option available for all the color mapping types. And we have rain hard color mapping, which is the default option and the most powerful color mapping type. Rain hard is a blend between exponential and linear multiply. Basically a hybrid algorithm that combines both linear and exponential color mapping. The degree to which one method or the other is applied to the image is specified by the burn value parameter. So if the burn value is set to 1, linear multiply will be used, and if set to 0, exponential will be used. And any in-between values will combine the two, obviously. Now let's take a look at a few renders with the rain hard color mapping and different burn values. In the first render, burn value was set to 0, so we are basically using exponential color mapping. In the next render, burn value was set to 0.15, then 0.25. Now we are using a combination of exponential and linear multiply color mapping. But because burn value is closer to 0, exponential color mapping is still the dominant one. In the next render, burn value was set to 0.5. Now both exponential and linear color mapping contributing half and half. And finally, burn value was set to 1, which is the same as linear multiply color mapping. For now, let's set the burn value to 0.15. Another parameter available in the Reinhardt type is multiplier, and this is a general multiplier for the color before they are corrected, and basically an overall brightness control for the entire image. In the first render, multiplier was set to 0.01, so we get a very dark image. And in the next render, multiplier was set to 1, which is our normal render, and in the next one it was set to 2, and we get an overall brighter image. Let's set the multiplier to 1 for now. In the linear exponential, HSV exponential, and intensity exponential, we have two parameters named dark and bright multiplier. The dark multiplier specifies the multiplier applied to the dark color values, and bright multiplier specifies the multiplier applied to the bright color values. For now, let's change the type to linear and set the bright multiplier back to its default value of 1 and take a look at a few renders. In the first render, bright multiplier was 1, the next one was 0.75, then 0.5, then 0.25. You can see it takes the bright pixels of the image, and each time we decrease the bright multiplier, those bright pixels become darker, but the darker pixels stay unchanged. And if we set the bright multiplier to be more than 1, those bright pixels even get brighter. Let's set the bright multiplier to 1 for now. As I said, dark multiplier specifies the multiplier applied to dark color values. In the first render, dark multiplier was 1, then 0.5, and finally 0.2. As you can see, the engine takes the darker pixels and multiply them by this value, and each time we decrease dark multiplier, those pixels become darker and darker, and if we use a dark multiplier higher than 1, those dark pixels get brighter. For now, let's set the dark multiplier to 1. Next we have gamma, and if I quote V-Ray's guide, it controls the gamma correction for the output image regardless of the color mapping mode. For example, to correct the image for a 2.2 gamma display, set this parameter to 2.2. Subpixel mapping specifies where the color mapping is going to be applied, whether at the pixel level or if you enable subpixel mapping at the subpixel level. And to get more correct result, it's recommended to have this option off. We have clamp output, which clips or clamps the very bright and high values, and the clamp value here specifies level of the cutoff of the information by the clamp output. And if you don't need that very dynamic range of information, or there is an artifact produced by the image sampling, for example, you can clamp the values, but generally it's a good idea to have those high dynamic range information and leaving clamp output disabled. In the first render, clamp output is off. In the next render, it was on and set to 1. And even though the image looks the same as our previous render, which was clamp output off in it, if I right click on this very bright spot, you can see the float values are not exceeding 1 in the brightest parts of the image. But in the previous image with clamp output off, we get very high values like 4, 6, even 11. Even though our monitor cannot display those ranges, but in the render with clamp output set to 1, we have limited the range from 0 to 1. And in the final render, clamp output was set to 0.5. Now let's set the clamp output to 1 and turn it off completely. Also, let's set the color mapping to Reinhardt and burn value to 0.15. We have effect background, so whether the color mapping affects background colors or not. In this case, the background is the V-Ray sky in the environment slot. We have mode options, and let me quote V-Ray's guide for this and go through the renders for each mode. as I explained them. Here mode basically specifies if color mapping and gamma are burned into the final image. This option replaces the don't affect colors adaptation only parameters from previous V-Ray versions. Color mapping only, no gamma. Only color mapping is burned into the final image and not gamma correction. This is the default option. V-Ray will still proceed to sample the image as though both color mapping and gamma are applied, but will only apply the color correction to the final result. Color mapping and gamma, in this mode both color mapping and gamma are burned into the final image. This corresponds to don't affect color parameters set to disabled in previous V-Ray versions, and we have none or don't apply anything. Basically neither color mapping nor gamma are burned into the final image. However, V-Ray will proceed with all its calculations as though color mapping and gamma are applied. This can be useful, for example, if you know that you will apply some color correction to the image later on but wish to keep the rendering itself in linear space for compositing purposes. This corresponds to don't affect colors parameters set to enabled in previous V-Ray versions. Okay, so that's about modes. And finally we have linear workflow, and this one is a legacy option as well, and both 3ds Max and V-Ray are by default set up with proper linear workflow in mind, and you don't need to enable this option at all. Perfect. So in this lesson we discussed color mapping, and I will see you in the next lesson. In this lesson we explore V-Ray Virtual Frame Buffer. Basically, V-Ray Virtual Frame Buffer, or VFB, is a display window for V-Ray renders that include a number of V-Ray specific features which is not available in the 3ds Max frame buffer or 3ds Max rendered frame. And we'll learn all about these capabilities in this lesson. For now, let's open up the render setup window, and under V-Ray tab we have a frame buffer rollout, and here you can control some aspects of the frame buffer and also control how and where to save your final render. Using show last VFB button, you can open up the VFB window and take a look at your last render. And this is exactly the same as the last VFB button in the V-Ray toolbar. Enable built-in frame buffer is what allows us to render into the V-Ray virtual frame buffer. And if I disable it and render the scene, the rendering will be done in the 3ds Max's frame buffer and not V-Ray's frame buffer. Let me enable it again. Memory frame buffer, when enabled, creates the V-Ray frame buffer and lets you see the rendering process and generated image. And this process requires some memory. But if you are rendering a high resolution image and you have tons of render elements and the scene is very complex and heavy and consumes a lot of RAM, to save some memory you can disable memory frame buffer and enable V-Ray raw image file, and then define where you want to save your render. And this way you don't get a feedback while rendering in the frame buffer. However, the image will be saved when the render is finished, and this way you get your final image and actually save some RAM but without any live feedback in the virtual frame buffer. So if I disable a memory frame buffer and start a render, you can see the engine is rendering the scene, but there is no live feedback of the process in the frame buffer. But if V-Ray raw image file was enabled and we had defined where to save the file, the render would have been saved in that path. So memory frame buffer option is here in case you are working with a heavy scene or a big final render and need to save some RAM. Let's make sure it's enabled for now. We have get resolution from max, and it is enabled by default, and that's why V-Ray frame buffer takes the render resolution from the common tab of the render setup window. And if I want to set the render resolution from this rollout, I can simply disable get resolution from max and define the desired render resolution and pixel aspect ratio. I want to talk to you quickly about the most optimized way of rendering your final image in V-Ray and whether to specify the resolution here or in the Common tab. Obviously, when we are rendering with 3ds Max, the render will happen in the 3ds Max's frame buffer. And when using V-Ray, virtual frame buffer will be used. But due to some technical issues, even when rendering into V-Ray's frame buffer, V-Ray still needs to create 3ds Max's frame buffer, even though the engine wouldn't send any data to 3ds Max frame buffer and all the information will be sent to V-Ray frame buffer. But that initial effort will cost some memory, so this is how Chaos Group suggests we approach rendering. In the Common tab, set the output dimension to a very low value. In this case, we have an image aspect ratio of 1, so let's set the width and height to 100 and 100. In the render output group, disable rendered frame window, which is 3ds Max frame buffer. Now under V-Ray tab and virtual frame buffer rollout, make sure get resolution from max is disabled. Now you can define the resolution, which was 800 by 800. And now if you start the render, you are gonna have some optimized experience and rendering. Let me stop the render for now. In the render elements tab, you can see we have some render elements defined here. We're gonna be using them in a moment. Let's get back to the V-Ray tab. Next we have V-Ray raw image file, and when enabled you can directly save out your render to disk without storing any data in the RAM if you are using bucket image sampler, obviously. For now, let's enable it and let's save the file in the render output folder for this lesson. In the final render folder, and let's name it Blue Room or whatever. In this case, let's choose OpenEXR as the format. Now if you want to save the render in the 32-bit space or as deep EXR, you can enable them here, otherwise the render will be saved as a 16-bit image. For now that's okay, and I press save here. This will save out all the render elements in one EXR file that you can later on extract it in Nuke or After Effects or any other application that you have. Now, if we disable memory frame buffer, obviously we won't see the live feedback of our render in the frame buffer, which is very cool if we want to save some memory. So let's disable it for now. But we can utilize this generate preview option, which creates a small preview of what is being rendered. So let's render the scene and see what we get. As you can see, we get a small preview of the render, and we only have this RGB preview pass to look at while the scene is being rendered. Now that the render has finished, if I open up the folder that we saved the render to, we have an EXR file containing the beauty pass and all the render elements that can be extracted later on, and we discussed this in the render elements lesson. For now, let's disable V-Ray raw image file and enable memory frame buffer. If you want to save out all the render elements into separate files or images, you can enable separate render channels option. For this to work, you need to have memory frame buffer enabled. Now you can use the browse button and define where you want to save the files. Let's go to the final render folder of this lesson, which is in the render output folder of the project file folder. and name it Blue Room Separate or whatever you want. This time let's use JPEG as the output format and press save. And in the JPEG image control window, just press OK. Also in the rollout you have this save RGB and save alpha options, which if you disable them, the RGB and alpha channels won't be saved and only the render elements will be saved out. Now if we render the scene, all the render elements and our beauty and alpha passes also will be saved out in separate files to that final render folder that we define. Let's render the scene and see what happens. We get our full live feedback in the frame buffer. We have all the render elements to look at. For now, let's wait for the render to be finished. Now that the render has finished, if I open up the destination folder, as you can see now we have all these separate JPEG or JPG files for each render element. For now, let's disable separate render channels and take a look at the Vary frame buffer interface itself. First, let's add this current render to the history list so we can access it later on. Also, let me double click on this final render and load it in the virtual frame buffer. Also, let's hide the history window so we won't get distracted. Up here we have the Vary virtual frame buffer or VFB toolbar. On the left side, using render elements dropdown, we can select any of the available render elements. Using R, G, and B buttons, you can define which of the red, green, and blue channels to be visible, or all of them. You can switch to the alpha channel or switch to the monochromatic mode. Then you have three very useful save options. The first icon is for saving the current channel or render element. So it only saves the active render element in the view. Let's click on the save button. Let's create a new folder inside this final render folder and maybe name it VFB. And let's name this render final render. And this time choose PNG as the format. Press save, then OK. Now as you can see in the destination folder, the current render has been saved out as PNG. The second save option is save all image channels to separate files, which obviously saves all the individual render elements into separate images. So let's click on this button, choose JPEG for the format and name it final render separate. Now press save, then OK. If I click on the save button again, you can see all the individual render elements are going to be saved as JPEG images. Okay. Finally, you can save all the image channels to a single file. So let's choose this save option. And in the VFB folder that we just created, let's name it something like final render all in one. Choose OpenEXR or Viewer image as the format. and press the save button. Now if I go to the destination folder again, all the channels has been saved in one EXR file that can be extracted later on in your compositing application. Next we have load image, which lets you load any image in the frame buffer, and sometimes I find myself using this option to load reference images. Using clear image, you can clear out the current content of the frame buffer. It's not gonna delete it from the history list if you have already saved it there, but it's just gonna clear the current content of the frame buffer window itself. So maybe let's clear the current render and we can load it again from the history list if we want to. And this option can be useful sometimes to avoid confusion with previous renders. We have duplicate to max frame buffer, which creates a duplicate of the current render in the 3ds Max frame buffer. Track mouse while rendering forces V-Ray to render the closest bucket found to the mouse pointer. So if I start the render and enable this option, you can see wherever the mouse is, the closest buckets around it will be rendered. And by the way, the render is so fast because I've increased the noise threshold to about 0.1. So we're gonna get this fast renders, but it's very noisy. Now let me stop the render and disable track mouse while rendering. Also, let's clear the frame buffer using clear image command. Next we have region render, which lets us to render the specific region that we need. So let's select any region in the scene by clicking and dragging. And now if I press the render button, only this region will be rendered and the rest of the image will be ignored. Next we have link VFB to PD player. PD player is an image viewer with some advanced functionalities by Chaos Group. We have some comparison options. What we can do in the history window is to define two images as A and B images. Maybe let's use this shade 7000 as image A and this incandescent 3200 as image B. Now compare horizontal is enabled and we can compare those two images. We can change it to a vertical comparison, or using this other tool, swap and AB images. Let me disable comparison for now. And using these last two buttons, we can start and stop the render, obviously. The next thing I want to talk about is the history window, which you can enable it using this show virtual frame buffer history window. The V-Ray virtual frame buffer allows the user to keep a history of previously rendered images, which is extremely useful. First, you need to enable history using this button. On the right side, you have this menu, and if you click history settings, you can define where the images in the history list will be saved on your disk, and also define a maximum size of the history images on the disk. I think by default it's something about 100 megabytes, but you can increase it like me if you want to save more renders in your history list, especially if you have render elements and you are rendering high resolution images. This 100 megabytes can be reached in a few renders. Okay, we have the save option, which saves the current image in the frame buffer to the history list. So if I just press save, you can see the current image has been added to the history and I can visit it later on. Then we have load, which loads the image selected in the render history to the virtual frame buffer. You can do the same by simply double clicking on the image in the history list, or right clicking on the image and choosing load. Using the remove button, you can remove the selected image from the render history, or you can simply right click and press delete. And we have A and B, where you can select your desired image and press one of these buttons to define it as image A or B for image comparison that we did a few moments ago. And if you right click on any of the images in the history list, you get some very useful options. Edit comment lets you add a text comment to the image, and it can be very useful later on, and I have been using it throughout this course. Now, load V-Ray settings, which basically sets the current render settings to the ones used to render the selected image. And obviously this option is very useful, and if you remember throughout this course I've been telling you that, for example, this render, you can simply right click on it and choose load V-Ray settings, and the settings that was used to render this particular image will be used in your render setup dialog, which will be very, very useful. We have compare V-Ray settings, which shows a table with the differences between the settings used to render this selected image and the settings that are currently set in the V-Ray renderer. And we have load color corrections, which loads the virtual frame buffer color corrections control from the selected image. And we have reload history, and this basically rereads the history image list, and this may be useful if the history folder is updated outside of 3ds Max or something like that. Now let's take a look at the color correction controls here. First, let's load the final render from the history list. To access color correction controls, you need to enable show corrections control on the lower section of the interface. And now you get some very basic but extremely useful color correction options. Using the global button up here, you can save the current state of all the color correction tools to be reused later on, and using load, you can load the file that you have previously saved. Also, you can do the same for each of the corrections individually using this menu on the right side of all the corrections. You can reset them to their default state as well using this reset option. To enable a certain correction, simply check the empty checkbox on the left side of the color correction name. As we have been using these correction tools throughout our course, I'm going to be very fast and quickly just take a look at them. Exposure, we have the exposure, which basically gives us a bunch of options. We have exposure controls, which controls the overall exposure of the render, and each step basically will make the render twice brighter or darker. So from 0 to 1, the scene gets twice brighter, and from, let's say, 2 to 1, the scene gets twice darker. Highlight burn selectively adjust the exposure of only bright parts of the scene, and contrast increases or decreases the overall contrast of the render, obviously. Now let me reset the exposure and disable it. White balance, as we have discussed earlier, just adjust the white balance of the render. Hue and saturation basically is to shift the colors of the image or control the overall saturation or lightness of the render. Using color balance, we can adjust the overall tone of the image in the shadows, midtones, and highlights of the image. Altogether, when all is selected, or individually adjust the tone of the shadows, midtones, and highlights of the image. We have used this correction numerous times during the course, and I assume you are quite familiar with how it works. And we have a level and a curve correction that work like the same exact tools in Photoshop. In this case, let's add some contrast using the level adjustment by making the low and high values to be close to each other. Let me disable levels. We can possibly get a better result if we use the curve correction. To add point to the curve, simply control click, or you can right click on the point to change its type, or select the point and move it around, or shift click on it to remove it. It's a bit hard to use a curve correction when you cannot individually adjust the red, green, and blue channels, but these correction tools aren't supposed to be complete. These are just some basic adjustments, and you're probably gonna do your main color correction work in a software that's designed to do that specifically. We have background image, and this allows you to load an image and use it as a background for your rendering, and you're probably gonna do that again in post, but here is a tool just to test what it's gonna be looking like later on. Right now V-Ray Sky is our background. Let me open up environment window and disable use map and render the scene again. Now that the render is finished and we don't have any background, if we enable background image, we can choose an image to be used as the background of the render. In the images folder, let's use this sky image. And as you can see, it's being used as the background image. If you enable as foreground, the image will be on top of the render. Let's disable background image and load the final render again. And finally, we have LUT, OCIO, and ICC color corrections, and these allow you to load an LUT, OCIO, or ICC color profile and color correct your image based on the information in those color profiles. In this case, let's enable LUT, which stands for lookup table. Click on the load button, and in the render output folder of this lesson, there is a .cube file which you can load here. Now this file tries to color correct the image based on the .cube file, and if I just disable this convert option, we might be able to see what this .cube file is trying to do. Any correction done with the LUT, OCIO, or ICC corrections can only be previewed in the frame buffer and won't be saved with the image. Let's disable all the corrections for now. In the lower section of the V-Ray frame buffer, there are a bunch of options that we haven't discussed yet. Force color clamping forces color clamping in the V-Ray virtual frame buffer. Show pixel information. If enabled, it always opens the info window, which will give you information about the pixel you right-click the mouse pointer on. If you right-click the mouse pointer over a pixel without turning this setting on, you will see the info dialog only while your mouse button is down. Then we have different color correction tools that we discussed a moment ago. We have display colors in sRGB space, which displays the image in sRGB color space. Click and hold the left mouse button to switch between sRGB color space and ICC. Use LUT correction, which enables and disables the effect of the lookup table loaded in the color correction settings. You can hold down to choose between LUT and OCIO color corrections. We have the show VFB history window. Use pixel aspect, which enables visualization of the pixel aspect ratio. We have the stereo button to preview the stereoscopic effect if available, which we discussed it in the camera section of the course. And we also have the open lens effect settings that we also discussed in the camera section. Using this small button, you can open up the V-Ray message window, which we discussed it in a later lesson, and you can also show the stamp controls and apply the stamp, which we'll also be discussing it in a later lesson in this section. Perfect. In this lesson, we learned about the V-Ray virtual frame buffer, both its settings in the render setup window and its interface. See you in the next lesson. Okay guys, in this lesson we take a look at the global switches settings under the V-Ray tab. So let's open up our render settings and see what we have. As most of these options are extremely self-explanatory, I'm not going to explain each option using examples unless it's necessary. First of all, let's set the interface to expert so we can see all the parameters here. We have displacement, which globally enables or disables displacement mapping. If you have tons of your displacement modifiers in your scene or in your viewing materials and you want to turn off all of them at once, you can use this option. We have force backface culling, enables or disables backface culling for camera and shadow rays. When this option is enabled, the surfaces of objects which are turned away from the camera will appear fully transparent. We have lights which turn on or off the lights that are already enabled in the scene. Hidden lights, this option controls the hidden lights in the scene. If you have hidden bunch of lights in your scene but they are still enabled in the modify panel, this option decides whether those hidden but enabled lights will be included in the render or not. If hidden light option is enabled, those lights will be included in the render, and if disabled, they won't be. We have shadows, which enables and disables the calculation of shadows in the render. Default light controls the state of default lights in the scene. By default, it's set to off with GI when basically when global illumination is disabled and we don't have any other lights in the scene, there would be a default light to lit the scene. And if set to off, the default lights will be off always no matter what. And if set to on, default lights are always switched on when there are no lights in the scene. So if I turn off all the lights in the scene by disabling the lights option and set the default lights to on and render the scene, you can see even though all the lights are off, we get the default lights to lit the scene. Let me stop the render and turn on lights and set the default lights to off with GI. Show GI only. When enabled, only the global illumination or indirect lighting will be shown in the final render. If I open up the frame buffer in the first render, show GI only is turned off, which is the default state, and in the second render it is turned on and we only get indirect lighting, basically only global illumination. Let's disable show GI only. Next we have probabilistic lights, and if I quote via guide, this option enables optimized sampling for scenes with many lights. When this option is disabled, Vray goes through each scene light and evaluates it at each hit point. In scenes with many lights and lots of GI bounces, this leads to a lot of shadow rays being traced and rendering can become extremely slow. This option makes it possible to render images that would otherwise take a very long time, at the expense of possibly introducing more noise into the rendering. When this option is enabled, Vray randomly chooses the specified number of lights and evaluates only those. Lower values make the rendering faster, but potentially more noisy. Higher values cause more lights to be computed at each hit point, thus producing less noise but increasing render time. End of quote. In this scene, if I go to the perspective view, we have about 210 sphere lights. Now let's take a look at the few renders with and without probabilistic lighting. In the first render, probabilistic lights is off, and in the second one it is on. I used progressive image sampler and the render limit was 3 minutes for both of these two renders, and as you can see in the render with probabilistic lights on, we get a cleaner render. Next we have don't render final image, and we use this in the GI section, and when this is enabled, only the GI maps like irradiance map, light cache will be calculated and the final image won't be rendered. We have reflection refraction, and when disabled, neither reflection nor refraction will be calculated in the final render. Maps enables or disables the texture maps used in the scene. In the first render, maps option is on and we get our textures in the render, and in the next one, maps is off. Let's enable it for now. Filter map enables or disables texture map filtering. We have filter maps for GI, which enables or disables texture filtering during calculation of GI and glossy reflections and refractions. When disabled, texture maps are not filtered for GI and glossy reflection refractions in order to speed up the calculations, and if this option is enabled, textures will be filtered. And GI filter multiplier is a multiplier for texture filtering for global illumination calculation. Override depth, if disabled, the reflection or refraction depth will be controlled locally within each material, and if enabled, none of the reflection or refraction depth in the materials can be higher than the value specified here. We have glossy effects. When enabled, all glossy reflections in the scene are replaced with non-glossy ones. And you can use this, for test renderings if you want to speed up the rendering in those phases. As you can see in the frame buffer, in the first render, glossy effects is on, and in the second one, it is off. And there is no glossy or blurry reflections in this render. Max transparency levels is the depth to which transparent objects will be traced. Now imagine if you had a leafy tree in your scene and you need a close-up shot from that tree, and leaves have a translucent material normally. You might need to increase the max transparency levels to see all the leaves. We have transparency cutoff, which controls when tracing of transparent objects will be stopped. If the accumulated transparency of array is below this value, this threshold here, no further tracing will be performed. And we have override material that we have used and discussed throughout the course. Basically, you can enable override material, define a material in this slot, and now all the objects in your scene will be rendered with that material unless you limit what the override material will be applied to using this include exclude list. Let me disable it for now. Max ray intensity suppresses the contribution of very bright rays, which may typically cause excessive noise or fireflies in the rendered image. Fireflies are those very bright individual pixels here and there. I think max ray intensity is on by default. For the next renders, I deleted 2/3 of the sphere lights in the scene. In the first render, max ray intensity is on and set to 20. And in the second one, it is off. You can see when it is off, we get very bright pixels here and there, and when max ray intensity is on and set to 20, we get rid of some of those very bright pixels or fireflies, but not all of them. In the next render, max ray intensity was set to 10, and now we get fewer of those fireflies. And in the next render, it was set to 5, which basically clears out those fireflies, even though possibly 10 would have been enough if we rendered the scene for a longer time. And if I compare the render in which max ray intensity was off and the one with max ray intensity set to 5, in that one, you can clearly see the difference. For now, let's set the max ray intensity to 5. Secondary rays bias is a small positive offset that will be applied to all secondary rays. This can be used if you have overlapping faces in the scene to avoid the black splotches that may appear. And we have legacy, sun, sky, and camera. And when disabled, which is the default state, V-Ray will use the improved and more accurate models. And if turned on, V-Ray will switch to the old sun, sky, and camera for, you can use it for compatibility issues if you loading an older scene or something like that. And we have 3ds Max photometric scale. When enabled, it aligns the V-Ray light, V-Ray sound, V-Ray sky, and V-Ray physical camera to the photometric units used by 3ds Max and its photometric lights. Okay, so that's about global switches rollout, and I will see you in the next lesson. In this quick lesson, we'll be taking a look at the environment rollout under the V-Ray tab. This is the current render that we have. There is no light in the scene. We only have an HDRI image in the environment slot. If I open up the environments and effects window. Now let's open up the render settings and go to the environment rollout under the V-Ray tab. And here you can override the 3ds Max's environment for global illumination, reflection, refraction, and secondary matte environments. If I enable GI environment override, for example, you can define a color to be used in the environment for global illumination calculation instead of the defined HDRI map in the environment slot of 3ds Max. And using this multiplier, you can multiply the color value, or you can define another HDRI or any other map instead of a color to be used. We have the same set of settings for reflection, refraction, and secondary matte environment. You can see we have this reflection refraction environment and a separate refraction environment. Right now, if I enable reflection refraction environment, the color or texture defined here will be used for both reflection and refraction rays, which is normally what you want. But if you want to have a separate environment override for reflection and refraction rays, simply enable refraction environment. And now the reflection refraction environment section will only be used for reflection rays, and refraction environment will be used specifically for refraction rays. And we also have the secondary matte environment. This group allows you to control the appearance of matte objects in reflections and refractions. For the GI environment override, let's use a pure red color with the value of 150. For the reflection environment color, let's use a pure green with the value of 150. And for the refraction, use a blue color with the value of 150. Now, if I render the scene with these new adjustments, the result would be render 01 in the frame buffer. What is happening here is that the GI rays do not see the HDRI map defined in the environment slot, but they see a red color as the environment. And if I go to the global illumination path, you can see how the red environment that the GI rays see affects the global illumination calculation. And the reflection rays are seeing a green environment instead of the HDRI map defined in the 3ds Max's environment slot. And if I go to the reflection path, this would be even more obvious. And the same thing for refraction rays. They are seeing a blue environment instead of the HDRI map defined in the 3ds Max's environment slot. And if I go to the refraction path, this would be even more obvious. Now let's try something else. If I open up the material editor, I have 3 HDRIs that I want to use instead of the simple colors. For the GI environment, let's use this first HDRI. For reflection environment, use this second HDRI. And for refraction environment, use this third HDRI. Now, as you can see in the render 02, and if I go through different passes, you can see different rays are using different HDRIs. If you are using the environment slot instead of the very dome light to lit your scene, to save some memory, you can define a less detailed HDRI in the GI environment and use a higher quality HDRI in the reflection and refraction environment. Okay, in this lesson we learned about environment rollout. See you in the next lesson. Okay guys, in this lesson we learn how to generate caustics in V-Ray for 3ds Max using the caustics rollout under the GI tab in the render settings. The technical definition of caustics in optics is the envelope of light rays reflected or refracted by a curved surface or object, or the projection of that envelope of rays on another surface. In order to calculate the caustics effect, V-Ray uses a technique known as photon mapping. It is a two-pass technique. The first pass consists of shooting particles or photons from the light sources in the scene, tracing them as they bounce around the scene, and recording the places where the photons hit the object surfaces. The second pass is the final rendering, which is when the caustics are calculated by using density estimation techniques on the photon hits stored during the first pass. Now let's see what do we have in the scene. We have this curvy object which is gonna be generating the caustics in the scene, and it has a blue refractive material applied to it. Right now we have two active lights in the scene. The main light that is coming from the right side and a fill light on the left side. And this is the render that we get from the current setup. There are a few steps we need to take in order to see some caustics in the scene. First, we need to go to the render settings window in the GI tab and caustics rollout, enable caustics, and this is going to be the first step. Next, in the material editor, select the material that is applied to your 3D object and make sure Effect Shadows is disabled. This is necessary to get physically accurate caustics. The next essential thing is a direct light source, either something like a sunlight or a directional area light. Let's try a directional area light. If I go to the perspective view, and this is basically our main light, and in order to make it generate some caustics, we need to make it a directional area light. If we try to increase the directional value under the rectangle disk rollout of the light, it would obviously affect the lighting in a way that is definitely not desirable for us, and most likely we want the lighting to stay the same. So we are not going to use this light as a caustic source or caustic generator. In fact, I'm going to select the light, right click and choose V-Ray properties and disable generate caustics for this light completely. Now this light can't generate any caustics. What I'm going to do is to select the light, right click in the Scene Explorer and choose Clone as a copy and name the light V-Ray light underscore main underscore caustics. So we know this is the light responsible for generating caustics. Now press OK. Now right click on the light and make sure that this light is generating caustics. The next thing would be to make sure it is directional. So let's increase the directional value to 1. And to make sure that the light encompasses the entire object, I'm going to increase its size to 100 centimeters. Also, as we don't want this light to affect the lighting at all, in the options rollout, we can disable effect diffuse, effect specular, and effect reflections. So even though the light does not contribute anything to the lighting right now, but it still generates caustics. Let's get back to the camera view, and if we render the scene right now, we should get some caustics. When you render your scene with caustics, there is a pre-calculation phase to build the caustic photon map that's going to happen before the GI calculations. And the resulting render would be render 01 in the frame buffer right now. Now there are a few obvious problems with this render. It's very splotchy and also it's very bright. There are a few ways to control how bright the caustics are, and the first thing would be to decrease the overall intensity of the light. In this case, let's select the light and reduce its multiplier to 15 from 16. And the splotchiness is coming from the lack of enough traced photons. If I right click and go to the V-Ray properties for this light, we need to increase the caustic subdivs, which controls the amount of photons that V-Ray will trace to estimate caustics. Large numbers slow down the calculation of the caustics photon map and may take more memory. Now let's try a few caustic subdivs value and see what subdiv value can give us a good result. For the first render, caustic subdivs was set to 1500. As you can see, it's very splotchy. For the next render, it was set to 6000. Much better, less splotchiness, but more noise. And for the final render, it was set to 12,000. It's cleaner. We just have some high frequency noise that can be dealt with the image sampler. And as you can see, because the pre-pass phase to calculate the caustics has increased due to higher subdivs, the render time is higher for this image compared to the previous render. Now let's go to the caustics rollout, set the interface to advanced, and let's see what we have here. First, we have search distance, and this is the distance around a given shaded point in which V-Ray searches for the photons. Smaller values produce sharper but perhaps more noisy caustics. larger values produce smoother but blurrier caustics. This value becomes less and less important as you increase the caustic subdivs of the light. So let's set the subdivs to a very low value like 75. And see how the search distance affects the caustics. In the first render, search distance was 1, then 5, and finally 50. As we increase the search distance, we get less noise and also less detail in the caustics. Let's set the search distance to 5 again. Next we have max photon, which is the maximum number of photons to be used inside the search distance. Smaller values result in a sharper but noisier result, and higher values produce smoother but blurrier results. Now let's set the caustic subdivision of the light to 6000 and try different max photon values. In the first render, max photon was set to 10, then 60, and finally 120. And by increasing the max photon each time, we get blurrier, smoother, and less detailed results. Let's set it to its default of 60. Multiplier value controls the strength of the effect on a global level. So if you have a few caustic generator lights in the scene, this value affects all of them. And if you want to control this multiplier on a per light basis, simply select the light and right click in the viewport and go to the V-Ray properties, and under generate caustic section, you can adjust this light's caustic multiplier. In this case, let's do it globally and take a look at a few renders. In the first render, multiplier was set to 1. In the second one, it was set to 2. And finally, it was set to 4. And obviously, each time we increase the multiplier value, we are going to get stronger caustics. Let's set the multiplier to 1 for now. Next, we have max density, and let me quote V-Ray guide for this. Max density limits the resolution and thus the memory of the caustics photon map. Whenever V-Ray needs to store a new photon in the caustics photon map, it will first check if there are any other photons within a distance specified by max density. If there is already a suitable photon in the map, V-Ray will just add the energy of the new photon to the one in the map. Otherwise, V-Ray will store the new photon in the photon map. Using this option allows you to shoot many photons and thus get smoother results while keeping the size of the caustic photon map manageable. In the next render, I set the max density to 0.1 and the light caustic subdivs to 18,000. And now we get this smooth and noise-free render, which it would have been very hard for the memory to manage a subdivision of 18,000 without using a max density higher than 0. And max density normally should be kept very low. For now, let's set the max density to 0 and caustic subdivision of the light to 6,000. We have direct visualization, and if I enable it and render the scene, we can see the calculation of the caustic photon map. Let me stop the render and disable it for now. We have mode, which controls the mode of the caustic photon map. When set to new map, a new photon map will be generated. It will overwrite any previous photon maps left over from previous rendering. When set to from file, V-Ray will not compute the photon map but will load it from a file. You can use this browse button to specify that file. And save to file saves out an already generated photon map in a file that you can later on load it using the from file mode and skip the calculation of the caustics map before rendering the final image. So when your render is finished, you can simply click this save to file and save the caustics, and change the mode to from file and load this file that you've just saved and render your scene without regenerating the caustics each time. We have don't delete, which if enabled, the photon map in memory after the rendering will be kept, otherwise the map will be deleted. We have autosave. When enabled, V-Ray will automatically save the caustics photon map to the provided file when rendering is complete. And switch to saved map. This is only available if autosave is on. It will cause V-Ray to automatically set the mode to from file with the file name of the newly saved map. And if you right click on any object in the scene and choose V-Ray properties, you get some caustics related options. We have generate caustics. This option needs to be enabled, so when the caustic generator light hit the object, the caustics can be actually produced. We have received caustics, whether the object receives caustics generated in the scene by other objects or not, and caustics multiplier, which is a multiplier for the caustics received by the selected object. And for the final render, maybe let's set the caustic subtips for the light to 18,000. Set the max density to something like 0.07. We can possibly use a lower max photon number like 40, 30 to get a bit sharp result, but I'll leave that to you. Let's add a V-Ray denoiser pass and set its preset to mild. And in the comment tab, set the resolution to 1280 by 720. In the V-Ray tab, set the image sampler to bucket, max subdips to 24, and noise threshold to 0.008, and render the scene. In the frame buffer, this is our final render. Let's check out the denoiser pass as well. You see, beautiful and clean. In this lesson, we learned about caustics in V-Ray. See you in the next lesson. Okay folks, in this lesson we are going to be taking a look at the settings tab of the render setup window. So let's open up the render setup window and go to the settings tab and see what we have here. We discussed default displacement rollout in the displacement lesson of the material section. We have system rollout, which contains a few sections itself, and we are going to be going through them in a moment. As always, let's set the interface to expert so we can see every single available parameter. In the first section, we can decide how V-Ray render regions or buckets are gonna go through the scene and render the final image. We have dynamic bucket splitting, and when this option is enabled, in order to use all the CPU cores for most of the render, V-Ray decreases the bucket size as the render is about to be finished. If you remember, the size of the bucket is being controlled from the bucket image sampler rollout, and right now it's set to 48. Now, if I get back to the settings tab and open up the frame buffer and select a small region to render, let's render the scene also. You can see when the dynamic splitting is turned on, and as we get closer to the completion of the render, the buckets are getting smaller and smaller, and this way all the CPU cores will be utilized all the time. But if I disable dynamic splitting and render the scene, the bucket size will be fixed at all times. Generally speaking, having dynamic splitting enabled is gonna speed up your renders a bit. Next, we have sequence, which controls the order in which the buckets are rendered, and the default triangulation sequence is the most optimized one. But we also have top to bottom. And if I disable region render in the frame buffer, you can see the top to bottom order of the buckets. And if I want to reverse the sequence, I can enable reverse bucket sequence down here. Now if I render the scene, the buckets are coming from the bottom part of the image. Let's disable reverse for now. We also have left to right. checker, spiral, the default triangulation, and Hilbert curve. For now, let's set it to triangulation. We have division mode. Right now, the render is divided into smaller buckets based on the size of those buckets, which is 48 pixels, right? But if I change the mode to count and in the bucket image sampler rollout, set the bucket count to maybe 2 and render the scene, now we are specifying how many buckets the image is going to be divided to. So right now, if I set the count or size to 1, only one bucket is rendering the entire image, and basically one CPU core will be used. And if I set it to 2, 4 buckets will be used. And if set to 4, 16 buckets will be used. So the square of this value here. Let's set it to 48 and in the system rollout change the division mode back to size. And now if I decrease the bucket size to, let's say, 16 and render the scene, we are gonna get very small buckets to render the scene. Okay, let's stop the render and set it back to 48 pixels. And get back to the settings tab, and we have previous render, and by default it's set to unchanged, and that means if we start a new render, the previous render will stay in the frame buffer until the new buckets take over the entire image. And we have a bunch of other modes. For example, if I set it to blue and start the render, the previous image in the frame buffer is going to be tinted blue, so you can simply distinguish the previous render from the current one. Let's set it to unchanged for now. Next, we have some parameters to control V-Ray's binary space partitioning tree, or BSP tree. As these parameters are pretty much advanced and you rarely need to touch them, and as I don't think I can explain it better than the chaos group, I'm gonna briefly explain these parameters from V-Ray's guide, and you can find more explanation of these parameters on the official V-Ray guide. First of all, what is V-Ray's binary space partitioning tree, or BSP tree? One of the basic operations that V-Ray must perform is ray casting, determining if a given ray intersects any geometry in the scene, and if so, identifying that geometry. We talked about ray casting in our previous sections. Now, the simplest way to implement this would be to test the ray against every single render primitive in the scene or triangle. Obviously, in scenes with thousands or millions of triangles, this is going to be very slow. To speed this process, V-Ray organizes the scene geometry into a special data structure called a binary space partitioning tree. The BSP tree is a hierarchical data structure built by subdividing the scene in 2 parts, then looking at each of those 2 parts and subdividing them in turn, if necessary, and so on. Now, those parts are called nodes of the tree. At the top of the hierarchy is the root node, which represents the bounding box of the whole scene. At the bottom of the hierarchy are the leaf nodes. They contain references to actual triangles from the scene. Now let's take a look at the parameters in this section. Dynamic memory limit is the total RAM limit for the dynamic raycasters, which store dynamic geometry like displacement, V-Ray proxy object, and V-Ray first strands, and so on. Default geometry determines the type of geometry for standard 3ds Max mesh objects. Note that some objects like displacements, mapped objects, V-Ray proxy, and V-Ray fer objects, for example, always generate dynamic geometry regardless of the setting. We have 3 geometry types. When set to static, all geometry is precompiled into an acceleration structure at the beginning of the rendering and remains there until the end of the frame. The static raycasters are not limited in any way and will consume as much memory as necessary. When set to dynamic, geometry is loaded and unloaded on the fly depending on which part of the scene is being rendered. The total memory taken up by the dynamic raycasters can be controlled by the dynamic memory limit parameter up here. And in auto mode, some objects are compiled as static geometry while others as dynamic. V-Ray makes the decision on which type to use based on the face count for an object and the number of its instances in the scene. Max tree depth is the maximum depth of the tree. Larger values will cause V-Ray to take more memory, but the rendering will be faster up to some critical point. And values beyond that critical point, which is different for every single scene, will start to slow things down. Minimum lift size is the minimum size of a lift node. We have face level coefficient, which controls the maximum amount of triangles in a lift node. If this value is lower, rendering will be faster, but the BSP tree will take more memory. We have use Embry, which if enabled, the Intel Embry Raycaster technology will be used, and this can really decrease your render time, and it is on by default. Now let me show you two renders with and without Embry. In the first render, use Embry is disabled and the render time was 1 minute and 46 seconds. And in the second render, use Embry was enabled and the render time was 1 minute and 28 seconds. So you can see how impressively using Embry Raycaster decreases render time. Next, use Embry for motion blur and hair, which determines whether to use Embry in calculating motion blur and hair strands or not. And we have conserve memory. If enabled, Embry will use a more compact method for storing triangles, which might be slightly slower but reduces memory usage. Next, we have the frame stamp section, and if I enable it here and apply it in the V-Ray frame buffer, it gives us this short bar presenting some selective information about the render, like V-Ray version that was used for this render or the render time. You can edit this information, add and remove any bit that you want using the frame stamp section or directly in the frame buffer. You can use insert variable to add different information to the stamp. In this case, let's add something like the date and the time of the render. And if I render the scene again, those information will be included in the frame stamp. And you can delete anything you want from here. Maybe we can delete the date and the time variables that we just added. Simply select and press delete. And in the render setup window, you can define the font or the justification of the text in the frame stamp and stuff like that. Let's disable it for now, both in the frame buffer and in the render settings. Next, we have distributed rendering, which is the process of computing a single image over several different machines. You can enable this capability here, and using the settings window, add and adjust the machines you want to use in the process. You can find a very detailed guide on how to set up distributed rendering in V-Ray on V-Ray's guide. So I'm going to skip that because it's going to be a long process. Next, we have V-Ray log parameters. When you render your scene, V-Ray writes out different information in a log file that is saved here. And you can define where the file is going to be saved. But we can see the essential part of that information in the V-Ray messages window. If I set the log window mode to always and render the scene, we get this V-Ray messages window containing different information and possible errors and warnings in the render. First, you can define when this window will be shown. You can set it to never, always, only on errors and warnings, or on errors. And using levels, you can determine what kind of messages will be showed in the window. One is, if you set it to 1, only error messages will be shown. If set to 2, error and warning messages will appear. If set to 3, errors, warnings, and informative messages will show. and if set to 4, all the messages will show up. Now let's set the log window to only on errors and warnings, and finally we have a few different parameters and options. We have low thread priority, and when enabled, V-Ray won't utilize all the CPU cores and you can use your machine for other purposes while rendering. And if disabled, V-Ray utilizes all the cores. We have check for missing file, and when enabled, V-Ray will try to find any missing files in the scene and will put up a dialog listing them if there are any. When optimized atmospheric evaluation is enabled, V-Ray calculates the atmospheric effect like fog first, and if it is opaque enough, the surface behind it won't be evaluated as it won't be seen in the final render anyway. We have shade context in camera space, and if enabled, V-Ray emulates work in camera space by converting the various points and vectors passed to and from other plugins. We have object settings, and you can access this window simply by right-clicking on any object in the scene and choosing V-Ray properties in the menu. We have been discussing most of these parameters throughout the course. Let's take a quick look at the remaining ones. And here you can mostly find per object controls of the motion blur, global illumination, shadows, and object visibilities in different rays. First, let's select any object from the list. On the left side, we have use default motion blur samples, and when enabled, the global samples for motion blur will be applied to the selected object, or you can disable it and define a motion blur sample value specifically for this object using the motion blur samples down here. And you can define motion blur duration specifically for this object. Using velocity channel and multiplier, you can manually specify a map channel to be used as a velocity channel and multiply that information. We can control whether the object generates and receives GIs or not, and by how much. We have GI surface ID, which prevents the blending of light cache samples across different surfaces. Especially if two objects have different GI surface IDs, the light cache samples of the two objects will not be blended. We have ray traced SSS ID, and simply the objects with the same SSS ID are going to be using the same illumination sample when using V-Ray fast SSS2 material, and when the multiple scattering mode in that material is set to ray trace. Subdivs multiplier is a multiplier for the subdivisions of all secondary ray tracing down for the selected object. We discussed caustics option in the previous lesson. We have some visibility options to control whether the object is visible or not for the GI reflection and refraction rays. Generate render elements. If disabled, this particular object won't be included in some of the render elements. And we have ignore in RT engine, and if enabled, the objects won't be included in the render when using V-Ray RT as the render engine. We have geometry, which allows the user to override the default geometry parameters in the system rollout on a per object level. We discussed matte properties in the V-Ray wrapper material lesson, I guess. We have trace sets. Reflection exclude list, which is an include exclude list that allows the user to specify which objects are going to be visible in the reflection of the current object. So imagine if you have a reflection or a reflective sphere and you don't want to see the reflection of a green box in it, you can set the mode to the exclude and add that box to the list, and this way that box won't be visible on the reflective sphere. Refraction exclude list is an include exclude list that allows the user to specify which objects are going to be visible in the refractions of the current object. So imagine if you have a book behind a refractive glass and you don't want to see the book behind the glass, you can add the book to the exclude list of the glass object. Let's close this window. We have light properties, and here you can control some global parameters on a per light basis. We talked about the caustics option in the previous lesson. We also have generate diffuse, diffuse subdiv, and multiplier. Generate diffuse, when enabled, V-Ray will generate diffuse illumination photon for the selected light sources. Diffuse subdiff controls the number of diffuse photons traced for the selected light, and diffuse multiplier is a multiplier for the diffuse photons. Now let me close this window, and we have a camera settings window which allows you to adjust the motion blur samples on a per camera basis if you want and have more than one camera in the scene. Next we have V-Ray presets window. Using this presets window you can save all the parameters and render settings that you have adjusted to a file and reload it whenever you want, and this can be very useful. Imagine you can have a test preset in which the settings are very low and you can render your scene very fast, and use this preset at the beginning stages of the project and have a final render preset with higher quality settings for your final render, and you can switch between those two sets of render settings by just one simple click. So let's see how we can save the current render settings that we have as a render preset. First off, let's name the preset and maybe something like test. Now on the right side, select which rollouts you want to be included in the preset. And let's select all of them and press save. Now as you can see, we have a test preset in the preset list, and it can be loaded anytime. Simply select the preset, choose the rollouts that you wanna be loaded from this preset, and then press load. And this way all the settings in these selected rollouts will be according to the information in the preset file. Let's close this window for now. In the texture options rollout, we have cache size, which specifies the size in megabytes of a separate texture cache to be used for tiled OpenEXR files. Note that the cache size cannot be decreased from its initial render value, and if you set it to a lower value, the value will not be used by Max until you restart the application. And we have clear cache on render end, which causes V-Ray to clear the texture cache after a frame is complete in order to avoid slowdowns. Okay, so that's about the settings tab, and I will see you in the next lesson. In this lesson, we explore VRT, even though we have used it several times in this course, but it's time to dig a bit deeper. VRT or VRT Real Time is an interactive rendering engine that can use both CPU and GPU. You can adjust your scene, your lights, your cameras, your materials, and see the result in real time. If I open up the render setup window, you can see VRT is available both as a production renderer, and if I change the target here, it is also available in the active shade mode. And you probably are going to use VRT in the active shade mode most of the time. So let's make sure the target is set to active shade and the render is set to VRT. And now we get a VRT tab where we can determine how VRT is going to handle the interactive rendering. The first thing you'll probably notice is we don't have as much parameters as when we were using VRAD or VREDU in the production rendering mode. For those parameters that are not available, VRT is gonna get them from the production renderer. And if you change the target to the production rendering mode and set the renderer to VRT, now in the VRT tab, you have a lot more tabs and settings that are similar to the VRAD or EDU. But in this case, if you try to render your scene in the production mode, you wouldn't have any interactivity and real-time rendering using VRT. It's just going to be a production render that will stop when the time limit or maximum samples per pixel has reached, and you might want to use VRT as your production render, you know, for its GPU capabilities, for example. But for now, let's set the renderer in the production rendering mode to VREDU or add, change the target to active shade mode, and make sure the render is VRT. Now we can start the render and see all the adjustments that we make in the scene in real time. So let's start the render. Select the main light, which is VRay light 001, and maybe change its multiplier to 30, or use a lower temperature like 4500 for its color. Maybe we can adjust the camera view a bit. So we can see all these adjustments in real time. Now, how fast and interactive this real-time capability is depends on your hardware. For now, let's set the multiplier of the light back to 10 and its color temperature back to 6500. And let's try to change our camera view back to what it was. Let's stop the render and get back to the V-Ray RT tab. Now, the first decision you need to make is what engine type you are going to use while working with V-Ray RT, whether CPU or GPU. And there are a few things to consider when you are making this choice. First, do you have the right hardware? Do you have a video card or video cards that support OpenCL or CUDA? Have you built your machine for CPU rendering or for GPU rendering? So if you know you have a very capable CPU, you're going to be better off using the CPU engine. On the other hand, if you know there is a powerful set of video cards setting pretty in your machine, you're going to enjoy super fast GPU interactive rendering. Generally speaking, when set to CPU, you are going to get a slower render, but because the video card is not engaged in rendering, you're going to have a responding user interface. But if you decide to go on the GPU route, the render itself is going to be very fast, but you are probably going to get a sluggish user interface, which can be a real nightmare. And another important thing is the CPU engine is gonna give you a more complete set of features, while GPU rendering still has more limitations. So when the engine type is set to CPU, the CPU engine is gonna render your scene, and you don't need any special GPU. We can set it to OpenCL, which in this case a GPU engine based on OpenCL is used. The engine uses graphic cards that support OpenCL and can be very fast depending on the hardware that you have. We have CUDA, which is a GPU engine based on the NVIDIA CUDA platform. This engine uses NVIDIA graphic cards that support CUDA and is the recommended engine for NVIDIA GPUs. The machine I'm using for recording this tutorial needs a serious upgrade, but it runs an NVIDIA GPU, so I can set the engine type to CUDA, and if I start the render, let's change the camera view a bit here and there. In this case, we get faster renders but more sluggish interface. So I know from my experience working with this machine that the CPU type is the best option for me. So let's set the engine type to CPU and take a look at the other options that we have. Let's run the active shade and go through its settings. First, we have the shading section. Trace depth is the maximum reflection and refraction depth of the materials in the scene. None of the materials can have a higher reflection or refraction depth than the value specified here. GI depth is the number of bounces for indirect illumination. Right now, Light Cache is our secondary GI engine, so this value is ignored and V-Ray automatically calculates the GI depths. We have auto update bitmaps. When enabled, V-Ray RT will try to automatically update the rendered image whenever one of the bitmaps used in the scene is changed on the disk. Use 32-bit frame buffer. When enabled, V-Ray RT will attempt to create a floating point 32-bit frame buffer which contains HDR information. We have lock render buffer, which is grayed out before starting the active shade, and if you enable it while running the active shade, no further changes to the scene are reflected in the RT, and the engine only refines the image, and as soon as you enable it, it becomes grayed out again, so you can't regain interactivity unless you stop the render and run the active shade again. Let's stop the render for now. We have override material, which overrides all the materials in the scene unless you exclude certain objects from being overridden by this material from this list. Let's use a simple gray material here as the override material. And if I start the render again, this material will override all the materials in the scene, and it can be very useful in the lighting phase of the project because it can really speed up the rendering. In the performance section, we have some very useful options. Array bundle size controls the number of arrays that are sent to the V-Ray RT render servers for processing. Larger sizes increase the speed of the render but decrease interactivity and vice versa, especially when you are working with GPU mode and you have a sluggish interface. You can decrease this value to regain some interactivity. Ray per pixel is the number of rays that are traced for each pixel during one image pass. The greater the value, the smoother the picture from the very beginning of the rendering with GI, but interactivity might be significantly diminished. And the same thing is true here, especially if you are working in the GPU mode to have a more interactive user interface. You can decrease this value, but it will result in a slower render. We have progressive RPP. When enabled, V-Ray RT starts rendering the image with a lower rays per pixel value and then progressively increases it. This speeds up the initial preview of the image. So if I render the scene while it is enabled, we get a very fast initial preview. But if I disable it and start the render, the initial preview is going to be slower. We have undersampling. When enabled, V-Ray RT starts rendering the image at a lower resolution in order to speed up the initial preview. Later, the image is rendered at its final resolution. So if I enable undersampling and start the render, you can see we get an immediate feedback, but in a lower resolution. And if I move my camera in the scene, as you can see, we get an immediate feedback, and I normally tend to enable this option while using V-Ray RT. We have show statistics, and if I enable it, we get some useful information on the upper right corner of the frame buffer, like V-Ray RT version, the number of calculated camera paths, and time elapsed since the current image started rendering. Let me disable it for now. In the next section, we have some rendering options. Max time is the maximum time for refining the image. Right now it's set to 0, so it refines the image until the noise threshold has reached. We have maximum paths per pixel, which specifies the maximum samples per pixel for refining the image. Max noise, which is the same as noise threshold in the image sampler settings, and it is a threshold that determines when to stop refining a pixel. We have in process RT engine, and when this option is enabled, the actual renderings of the image happens inside the 3ds Max process. This speeds up the initial scene translation phase and basically it improves the interactivity of active shade rendering. When disabled, a separate V-Ray standalone render server is launched in DR mode to perform the actual rendering. We have distributed rendering for V-Ray RT. You can enable it and use the render servers button to define the machines that will be used in the process. We talked about the engine section, and when set to CPU, all the other options are grayed out as they are GPU related. So let's change the engine type to CUDA for now. We have coherent tracing, and when enabled, V-Ray RT will attempt to spawn secondary arrays like GI reflection in similar directions in order to improve rendering speed on certain GPUs. We have GPU textures drop down. When set to resize textures for GPU, high resolution textures in the scene will be resized to a smaller resolution in order to optimize memory usage. And this parameter is only obviously available when type is set to OpenCL or CUDA, basically when GPU rendering is enabled. We have GPU texture size. When resize textures for GPU is enabled, this value specifies the resolution to which the textures will be resized. And we have the texture format that can be 816 or 32-bit. Let me set the engine back to CPU. In the geometry section, we can enable or disable certain types of geometries from showing up in the V-Ray RT. We have V-Ray proxy objects, and when enabled, the proxy objects will be rendered by V-Ray-RT. But in the GPU mode, the proxies are not going to save their purpose of saving memory. They're going to be rendered as normal objects, and we're going to be discussing V-Ray proxy in our next section, definitely. And we can enable or disable the rendering of XREF scenes and containers, particle systems, displacement mapping, and motion blur. Even though when RT used as a production renderer, motion blur parameter here wouldn't affect anything and the scene options will be used instead. We can also render stereoscopic effects using RT even if there isn't any very stereoscopic helper in the scene. So if I set the stereo mode to left and right and set the eye distance to something like 20 centimeters, so we can see the effects a bit better, and we know 6.5 is the standard value here, but now let's render the scene. We have three windows, a left view, a right view, and in the frame buffer we get both of the left and right eye images. And if I enable the stereo mode in the frame buffer, we can see the stereoscopic effect. Let me now disable it in the frame buffer. Now let's set the mode to anaglyph, red and cyan, and render the scene again. Now we have the left and the right eye images in the frame buffer and a separate window displaying a red cyan anaglyph of the stereo image. Let me disable the stereo mode for now. In the messages window, we can output diagnostic messages. So if I enable warn for non-physical features and unsupported features and render the scene, if there was a non-physical feature like an invisible light or an unsupported feature like hair and fur modifier, we would have seen a warning message in the frame buffer while rendering. So for example, if I select light 001 and make it invisible and start the render again, we get this green message that says there is a non-physical feature in the scene, the light is invisible. Let me stop the render and make the light visible again. And we have this message delay. When we start RT, we get some informative messages in white color in the frame buffer about the current stage of RT, and message delay is the number of seconds that information messages and warnings stay on the screen. You can set it to 0 to disable information messages completely. In the .vr scene export section, you can export your current 3ds Max scene to a .vr scene file, which is the scene description format used by the standalone version of V-Ray, and you can simply enable export .vr scene file, define where you want to save the file, and when you run the active shade, the scene will be exported. Or you can enable don't render, just export, and this way when you press the render button, the active shade won't start and only the scene will be exported to a .vr scene file in the specified location. And you can do the same thing in the scene. Simply if you right click in your scene, you can choose export .vr scene and export your scene in that way, and you get a bit more options, and we're going to discuss that probably in our next section. And if you change the engine to CUDA, you get a V-Ray RT render devices select rollout, where you can specify which video cards to use for rendering. So if you have multiple video cards on your machine, you can enable the video cards that you want to be used for RT rendering, and maybe disable another GPU so it won't be used in the RT rendering, and therefore will be free to handle the user interface, thus avoiding sluggish interface. Now if I set the engine to CPU and render the scene, if I right click in the frame buffer, we have some specific RT options. First we have real zoom, which lets us use the scroll wheel to zoom in, and it's like moving the camera in the perspective view. And double click again so we get back to our main view. We have view navigation. If enabled, we can navigate directly in the frame buffer by simply clicking and dragging. Pause lets us to pause the render and resume it whenever we want. And we can reinitialize the render using the last option. Perfect. So in this lesson, we learned about V-Ray-RT, and I will see you in the next lesson, which is probably going to be about render elements. So see you there. In this rather long lesson, we are going to be learning all about render elements. The topic in hand can be discussed in depth over several hours, but here we need to go through it in one lesson. If I open up the render setup window and go to the render elements tab and click on this add button, we can see a list of the available V-Ray render elements. Now, the first question we need to ask ourselves is why we use render elements in our renders. There are so many reasons for that, and as we go through some of these render elements and perform some compositing in an external application, you become more familiar with those reasons. But the main reason is that using render elements, we can break up our render into its constituents like direct and indirect lighting, reflection, refraction, and so on, and composite those parts back together in a compositing application like Photoshop, After Effects, Nuke, Fusion, or whatever you use. And having individual control over each and every component of our render gives us a lot of flexibility to adjust our final image without having to re-render the whole scene. Imagine we can take the reflection render element in our compositing application and make it stronger, or we can adjust the lighting in the scene and make it brighter or darker, or change its color maybe. We have four main render elements categories in V-Ray. We have our beauty render elements, which are the render elements that make the final beauty image. Elements like lighting, GI, reflection, refraction, speculars, and so on. We have our matte render elements, which help with the masking and selection of different parts of the image in compositing. Elements like multimatte, object, and material ID are in this category. Then we have our geometry render elements. These elements use the objects in the scene to produce geometry-based data. Passes like z-depth and velocity are in this category, and we can reproduce effects like depth of field and motion blur with them in the compositing stage. And finally, we have our utility render elements, which allow to see some information about how the rendering process is done, and also we can generate some useful render elements like ambient occlusion using the extra texture utility render element. Passes like sample rate and sample info are in this category. Now let's start with the beauty render elements and the more important ones here. Select alpha, V-Ray diffuse filter, global illumination, lighting, reflection, refraction, self-illumination, shadows, specular, SSS2, total lighting. Now coming back to the upper section, we don't have any atmospheric effects like environment fog in the scene, so I'm gonna skip that for now. Add V-Ray background. We don't have any caustics in the scene. Now let's add all the raw elements like raw global illumination, raw lighting, raw reflection, raw refraction, raw total lighting, and V-Ray reflection and refraction filter. And finally, V-Ray light select. Now that we have all these beauty render elements selected, let's press OK. The order you select these passes does not matter at all in compositing, just how they appear in the frame buffer. The only render element we need to adjust before starting the render is going to be V-Ray light select. The light select render element represents the lighting contribution from one or more selected lights in the scene. So we can basically break up the lighting in the scene using this render element. We need a few light select render elements for the different light sources in the scene. If I select the light select render element and come down to its parameters, we have this lights list where we can define a light or a group of lights, and this way we get to see the contribution of that particular light in this render element. If I open up my light group in the Explorer, let's first click on the add button and add V-Ray Sun. Also rename this render element to V-Ray light select underscore sun. Now add another light select render element and rename it to V-Ray light select underscore portal. Click on the add button, press H and pick all the portal lights in the scene, the lights that are in the windows. And finally add another light select, rename it to V-Ray light select candle, and add all these small spherical lights around the candles. Now we are ready to render our scene. We can see the result of this render in the frame buffer. So first let's take a look and explain the most important beauty render elements that are used in compositing to reconstruct the final image. The first one is V-Ray diffuse filter, and in this render element we get the flat colors and textures used in the material without any lighting or shading information. Any other render elements that include colors and textures from the materials, or basically have some diffuse component, it gets that diffuse component from the V-Ray diffuse filter render element. V-Ray diffuse filter might not be used directly in compositing, but it helps to reconstruct other passes. For example, take a look at the V-Ray lighting pass, which has both the direct lighting and diffuse color information. That diffuse color information is coming from the V-Ray diffuse filter element. If I go to the V-Ray raw lighting pass, we just have the direct lighting, there is no diffuse color information. But to get the main lighting pass, we will multiply the raw lighting pass by the V-Ray diffuse filter pass, and we get our final V-Ray lighting pass. In the compositing process, we can directly use the lighting source or the lighting pass, but if we want to have even more control, we can generate our lighting pass by multiplying V-Ray diffuse filter and V-Ray raw lighting pass, and the same thing is true about the global illumination element, shadow elements, and so on. The next important pass is V-Ray lighting, and as I mentioned, this render element or pass stores direct lighting and diffuse color information, and you can use this pass in compositing to adjust the direct lighting. For example, make it darker or brighter, and as previously mentioned, this pass is generated by multiplying diffuse filter and raw lighting pass. The next essential pass is V-Ray global illumination, and here we have our indirect lighting or global illumination information, and you can use this pass in compositing to adjust the look of indirect lighting. And like the lighting pass, this render element is the result of multiplying the V-Ray raw global illumination pass by V-Ray diffuse filter pass. So if we want to have more control over our global illumination pass in compositing, instead of using the global illumination element directly, we can multiply those two previously mentioned passes together and get the same global illumination pass. Next we have reflection render element, and in this element we have the reflection information calculated from the material's reflection values in the scene. And you can use this pass to increase or decrease object reflectivity in the compositing. The reflection render element is formed by multiplying the V-Ray raw reflection render element by the V-Ray reflection filter render element. The objects in the V-Ray raw reflection render element are either fully reflective or not reflective at all and fully black. When we multiply this pass by the V-Ray reflection filter, which has different shades of gray, and the more reflective the surface, the brighter the color, we get our final reflection pass. For example, in the V-Ray raw reflection pass, both the floor and the wall are fully reflective, and in the V-Ray reflection pass, the wall has a dark color and the floor has a bright gray color. Now when we multiply those two passes, you get your reflection pass in which the floor is very reflective because remember it had a brighter reflection color, and the wall is not that reflective because it had a darker reflection color. Hopefully it makes sense. Again, in compositing, we can directly use the reflection render element, or to have more control, reproduce it by multiplying raw reflection and reflection filter passes. Next, we have our V-Ray refraction render element, and here obviously we have our refraction calculated from the refractive materials in the scene. And this pass can be used to change the look of the refractive objects in compositing. And as you probably have guessed by now, the refraction pass is formed by multiplying V-Ray raw refraction by V-Ray refraction filter. And you can either use refraction pass directly or the resulting composite of raw refraction and refraction filter passes in your compositing. Don't worry if it's a bit confusing. I'll be showing you practically how to composite these passes in After Effects later on in this lesson. Next we have V-Ray specular pass, and this is the specular reflection information calculated from the material's reflection values in the scene. This is basically the reflection of light sources in the scene. Next we have V-Ray shadow pass to change the look of the shadows in the compositing, to make the shadows darker or brighter. We have subsurface scattering render element, which stores the subsurface scattering information from both fast SSS2 material and V-Ray skin material. And you can use this pass in compositing to adjust the look of subsurface scattering. We have our self-illumination render element, and here we have the illumination data from self-illuminated objects that have V-Ray mesh light, or have a V-Ray light material, or a V-Ray material with self-illumination contribution will be stored here basically. Alpha render element shows the transparency of objects in the scene as grayscale colors. Solid geometries are represented by solid white, while those areas not blocked by geometry within the scene are black. We have our background render element, which is a simple V-Ray sky here that was set in the environment slot. Another interesting render element is V-Ray total lighting, and this pass includes both direct and indirect lighting. So in composite, instead of first adding the global illumination render element to the lighting render element, you can use the total lighting render element directly instead of the lighting and global illumination render elements. And total lighting render element itself is coming from multiplying the raw total lighting render element by V-Ray diffuse filter. We have also specified a few light select render elements to isolate the contribution of different light sources that we have in the scene. We have our V-Ray light select sun, light select portal, and light select candle, and these three passes combined together will give us the lighting render element. But now we can increase or decrease the contribution of each light in compositing without having to render the whole scene again. Another beauty render element that we have is V-Ray atmosphere, and this render element include atmospheric and volumetric effects like environment, fog, and aerial perspective. And just let me actually just quickly set up a quick example and add some fog to the scene. First, let's add V-Ray atmosphere render element. Next, open up the environment and effects window by pressing 8 or from the rendering menu. And if you come down to the atmosphere rollout, you can add an environment fog. We don't want such a dense fog, so we can increase the fog distance to 800 and fog height to something like 300, so it will cover the entire view. And let's also enable scatter GI. Also in the environment fog nodes section, let's disable use all lights and only use the sunlight to affect the fog. You can select these curtains and hide them also. Now if I render the scene, we get our next render with V-Ray environment fog, and this is our V-Ray atmosphere render element, and we can simply make the atmospheric effect less or more intense in compositing, or even change its color tint if we wanted to. Perfect. Let me close the frame buffer, unhide the curtains, and in the environment and effects window, select the V-Ray environment fog and disable it for now. And in the render elements tab, delete V-Ray atmosphere render element. Next we have our matte render elements, and these render elements help with demasking and selection of different parts of the image in compositing. And the way these matte render elements are used in compositing is, using them you can isolate certain object or surface with a certain material and apply the adjustments that you want, like for example any color correction, specifically to those isolated parts. Imagine if you want to change the color of the walls using a hue and saturation effect in Photoshop or After Effects. Using these matte elements you can mask the hue and saturation effect to only affect the wall and not the rest of the image. We have a few essential matte render elements. Let's add the more important ones. We have multi-matte render element, which is the most important one. We have V-Ray material ID or V-Ray MTL ID. We have V-Ray object ID, V-Ray render ID, and V-Ray wire color. Now press OK. For now, let me select the multi-matte element and rename it to multi-matte element underscore 01. Let's add a second multi-matte element and rename it to multi-matte element underscore 02. And change the RBuff ID to 4, GBuff ID to 5, and RBuff ID to 6. Sorry, BBuff ID to 6. In a moment I explain the reason for doing this. And if I render the scene, we have our matte render elements in the frame buffer. We have V-Ray object ID, which isolates individual object based on their object ID. You can see in the object ID render element, the walls, the floor, the chair, the desk, they all have different colors based on their object ID. In this case, if I select this wall and right click and choose object properties, the object ID for this wall is set to 1. If I select the floor and go to its object properties, I have assigned 3 as its object ID, and you can simply change it to whatever number you want. And the chair, for example, has an object ID of 4. So all the objects in the scene with the same object ID will have a differentiating color. In this case, for example, all the objects with the object ID of 4, like the chair, will have a blue color assigned to them in the object ID path. Now, very simply, in any compositing app like Photoshop, you can isolate the object that you want and adjust it without affecting other objects in the scene. And the object with their object ID set to 0 will appear black in the render element. We have material ID, and this path is basically doing the same thing, but instead of isolating the objects based on their object ID, it does so based on the material IDs. If I go to my material editor and pick the material from this frame object in the scene, for example, and right click on its name, the material ID for this material is set to 9, and the wall, the floor, the chair, the lampshade, they all have different material IDs. and the materials with the same material ID will be having the same color in the material ID render element. We have our render ID render element, which creates selection mask based on the node handle of each object, and we have the wire color render element, which stores the wireframe color of the object as set in 3ds Max Scene, and you can create masks based on the wire color of the objects in your compositing application. Next we have our multi-matte render element, which is the most important one and basically the most popular one, the easiest one to use in compositing applications to isolate the objects. The multi-matte render element creates red, green, and blue selection masks based on object IDs or material IDs. So this is our multi-matte render element 01 and this is 02. If I go to the render setup window again and select the first multi-matte render element and take a look at its options, we can define only 3 object or material IDs. Right now we are isolating objects with their object IDs set to 1, 2, or 3. You can see the R buffer ID is set to 1, so the objects with the object ID of 1 will have a pure red color. G buff ID is set to 2, so the object with their object ID set to 2 will be green, and B buff ID is set to 3, so the objects with their object ID set to 3 will appear pure blue in the multi-matte render element. With multi-matte, a single R, G, or B channel can be used directly as a matte, eliminating the step of selecting the color manually in the compositing software. This ease of use makes multi-matte a popular choice, and I'm going to show you in After Effects in a moment how easy it is to actually isolate an element using the multi-matte render element. If you want these IDs basically to be based on material IDs and not object IDs, you can enable Ease Matte ID option. You can add additional multi-matte render elements to isolate the other objects or material IDs. In this case, the second multi-matte render element isolates the objects with their object ID set to 4, 5, or 6. So that's about the most important matte render elements. Let's explore the utility render elements. We have V-Ray denoiser, V-Ray DR bucket or distributed rendering ID, V-Ray extra text, V-Ray illuminance, V-Ray sampler info, V-Ray sample rate, V-Ray unclamped color, and V-Ray option RE. First, let me select V-Ray extra text and use a V-Ray dirt map as its texture. Also select the sampler info and change its type to UVW coordinates. If you render the scene, the result would be the render named utility render element. First, we have V-Ray denoiser, and we have used it a lot in this course, and it removes noise. It's that simple, and it's doing such a great job. The denoising operation detects areas where noise is present and smooths them out. And if I compare the original beauty pass with the denoise pass, you can see how clean it gets. You are not supposed to use a high noise threshold while you in your image sampler setting and assume that V-Ray denoiser can clean up the excessive noise. If you do it this way, you are going to get obvious artifacts in the denoiser pass that makes it useless. You are supposed to use an acceptable noise threshold while you in your image sampler, maybe something like a 0.01 or 0.02, and leave the high frequency noise for the denoiser pass. And if I go to its settings, we have a bunch of presets: mild, default, strong, and custom. Default basically applies a mid-level denoising, mild applies a more subtle level of denoising than the default preset, and strong applies a stronger level of denoising than the default preset. Custom allows the strengths and radius parameters to be set to custom values. And strength is determining how strong the denoising operation will be, and radius specifies the area around each pixel to be denoised. A smaller radius will affect a smaller range of pixels, while a larger radius will affect a larger range, which will increase the noise removal. And we have update, which updates the denoiser pass based on the adjustments that we have made here. Let's maybe set the preset to mild and click on the update button. After a few seconds, we have an adjusted denoiser pass. Also, this pass creates some extra render elements like noise level and the focus amount to make the denoising operation possible. We have the distributed rendering ID render elements, or V-Ray DR bucket, which shows the name of the rendering machine that rendered any particular bucket when distributed rendering is used. In this case, we haven't used it, so this render element is black. We have our V-Ray extra texture or extra text, and this render element renders the entire scene with one texture mapped onto all objects in the scene. In this case, we used a V-Ray dirt map as the texture, and as you can see, it has been applied to all the geometries in the scene, and it gives us a beautiful ambient occlusion pass that can be used to enhance the details in the image in compositing. And you can drag the V-Ray dirt texture used as the extra texture and edit it in the way you want in the material editor. We have V-Ray Illuminance. The Illuminance render element is a grayscale or color image that displays the illumination in each part of the scene. We have V-Ray Sample Rate. The sample rate render element displays the work being done by the image sampler as a red, green, and blue image. We have discussed this pass and how to read it and use it in your image sampling in the image sampling section of the course. So you can check that lesson out if you are not sure what these colors mean. The sampler info render element provides information about various aspects of the shaded points, such as position, normal, bump normal, reflection, refraction, vectors, UVW coordinates, and so on. In this case, if I select the sampler info render element, we set its type to UVW coordinates, and that is what we see in the frame buffer. And these render elements can be used for diagnostic purposes or retexturing and relighting in compositing applications. Which unfortunately can't be covered in this limited time that we have, but you can search the web and see how these passes can be used in compositing. And we have V-Ray Unclamped Color. The unclamped color render element stores the images, colors, and textures with colors that have not been clamped. A number of settings and parameters in V-Ray, we know that they actually clamp colors so they fall within a particular range. This render element provides the unclamped version of the image. In the render setup window, we have V-Ray option RE or V-Ray render options, and this render element does not generate any render element, rather it controls some internal settings for V-Ray that are otherwise inaccessible. For example, using the EXR compression dropdown, we can specify the compression method when writing open EXR files through the V-Ray raw image file option in the V-Ray frame buffer settings. And finally, we have our geometry render elements. Geometry render elements rely on geometry to generate the render elements, and they include bump normals render element, normals, velocity, Z depth, and wire color. Wire color is technically a geometry render element, but as its main purpose is to aid masking and basically the selection process, I discussed it under matte render elements. Now let's add these render elements. So let's add these 4 render elements. First, bump normal, the normal, velocity, and Z depth, and press OK. Select the Z depth, set the Z depth min to 400 centimeters and Z depth max to 770 centimeters. We talk about the reason in a second. Also, if I go through the timeline, we have this very simple animated sphere which helps us to visualize the velocity render element. Let's stop it at frame 32 and take a look at the resulting render in the frame buffer. First, we have our bump normals render elements. This path stores the camera view as a normal map. The normals are generated using screen space, which uses the XYZ orientation of the camera view. And these render elements can be used to relighting purposes in compositing, especially the light that comes from a certain direction and needs to be adjusted. We have V-Ray normals, which is a render element that stores the camera space normal map using the geometry's surface normal. The normals render element is useful for adjusting the lighting in the composite. We have V-Ray velocity. This render element is a color or grayscale image that stores velocity information about objects that have animation in the scene, and this path can be used to produce motion blur in compositing. For example, in After Effects, you can use a plugin like a Smart Motion Blur, define this velocity path as the motion source, and this way add motion blur to the sphere without having to re-rendering the motion blur from V-Ray. And finally, we have V-Ray Z depth. This render element provides information about each object's distance from the camera in the current view. You can see in this case the polygons or objects that are closer to the camera are white, while those far away from the camera are black. We can control where exactly this white to black transition happens over the distance from the camera using the Z depth min and max value. In case of Z depth min, objects up to this distance from the camera will render as white, and in case of Z depth max, objects further than this distance from the camera will render as black. And obviously the transition from white to black happens from the distance defined in the Z depth min to the distance defined in the Z depth max. If I go to the top view and select my physical camera, you can see it has a target distance of 535 centimeters. We set the Z depth min to 400 centimeter, and if I put this value here, you can see this is the point before which all the objects will be white, and from this point the Z depth map starts to get darker until it reaches the Z depth max, which is 770 centimeter. And if I put it here as the target distance, you can see it is the end of the room, and from this point on everything is black in the Z depth map. And you want to make sure that all of your geometries in the camera view are located in a distance between the Z depth min and the max, so you can successfully reproduce effects like depth of field in your compositing application using this render element, obviously. Now let's set the target distance back to 535 centimeters and make sure the timeline is on frame 0. Now we have discussed all the render elements, and it's time to do some basic compositing in After Effects using these passes. In the Render Elements tab, I'm gonna first delete some of the unnecessary passes. From bottom to top, we can delete all the passes from V-Ray Velocity to V-Ray Illuminance, and also V-Ray Denoiser can be deleted. We can delete V-Ray DR buckets and render ID and wire color. Okay, we can delete all of these passes that we just selected. For the final render, let's go to the Comment tab and change the width and height to 1200. And in the V-Ray tab, change the type to bucket. Set the max subdivs to 32 and noise threshold to 0.007. Also in the Frame Buffer tab, enable V-Ray raw image file and go to the final render folder for this lesson, which is located in the render output folder of the project files. Name it a blue room or something like that. Use OpenEXR. I'm not going to enable 32-bit output, so we are basically outputting a 16-bit image. Now we can press save. Also, let's enable separate render channels. Go to the final folder again. And we have another folder called separate. Go in there and let's name it separate blue room. Choose OpenEXR as the format, press save, and in the configuration window make sure the format is 16 bits and press OK. In the GI tab, let's set the irradiance map subdepths to 85 and interp samples to 25 and set the light cache samples to 1500. Perfect. Now we can render our scene and start compositing in After Effects. Here we are inside Adobe After Effects. Obviously, we don't have the time to go through every trick in the book, but I'll be trying to cover all the basic foundations that you need to start your compositing journey. First, double-click in the project panel and go to where you have saved your render. In this case, we need to go to the final render folder of this lesson, located in the render output folder of the project files folder for this course. We have this EXR file called Blue Room, and it contains all the render elements. So let's double click on it and import it. Let me double click again in the project panel and go inside the separate folder. And here we have all the render elements in separate EXR files. Let's select all of them and click the import button, and while they are selected in the project panel, also let's drag them into a new folder. And we can name this folder separate or whatever you want. Sometimes the extractor effect in After Effects can be a bit buggy and might miss some render elements in the EXR file that contains all the passes. So in that case, these separate render elements can be very useful. Now, first, let's create a new composition based on our main EXR file. And rename the composition to basic composition or anything that you like. The next thing is to make sure we are working in the right color space. So from the file menu, open up the project settings window. In the color settings section, change color depth to 16-bit. If you remember, we rendered out 16-bit images. Change the working space to sRGB and enable linearize working space and press OK. In the Effects and Presets panel, search for the Extractor effect and apply it to the layer. Now if you click in this empty space in the Effects control window, we get the Channels window, where we can extract different render elements from the original EXR file. The first render element we need is lighting, so let's select V-Ray lighting and press OK. Now we have V-Ray lighting render element in the composition. Also, let's rename the first layer to lighting so we don't get confused. To rename a layer, simply select the layer and press enter, type the new name and press enter again to confirm the new name. Next, we need the global illumination render element. So let's duplicate the lighting layer by pressing Ctrl D. Rename it to GI, and from the extractor effect, select the global illumination render element. Now we can change the blending mode for the GI layer to screen. We can change the blending mode for the first layer to screen as well. So let's do that. But as it is the first layer, it doesn't really matter to use normal or screen render element. Next, we need our reflection layer. So duplicate the GI layer, rename it to reflection, and from the extractor effect, select reflection render element and press OK. Now let's add the refraction render element. The same process, duplicate the reflection layer, rename it to refraction, choose the refraction render element from the extractor, and now we have added our refractive surfaces to our render. The naming of the layer really doesn't matter, I'm just trying to stay organized here. You can see the render is coming together, and as we are duplicating the previous layers, the new layers blending mode is also set to screen. If not, you need to change blending mode to screen manually. You just need to add this layer together, basically, nothing very specific going on here. Now it's time for the specular render element, so duplicate the refraction layer, rename it to specular, and choose V-Ray specular render element in the extractor effect. Next, we can add the subsurface scattering render element. So the same process again, duplicate the layer, rename it to something like SSS, and select V-Ray SSS2 render element in the extractor plugin or effect. And finally, it's time for the self-illumination render element. Duplicate the layer, rename it to self-illumination, and choose V-Ray self-illumination render element. And here is our final render without the background. Now let me turn off the layers and go through the render elements we used to reconstruct our final render. First, we added our lighting render element, then global illumination, next reflection. After that, we added refraction, then specular, subsurface scattering, and self-illumination. Now we are back to our beauty render basically. In this stage, we can do a lot. For example, I really want to have a much stronger scattering effect, so I can simply select the SSS layer, apply an exposure effect, and increase the exposure value to something like 1. Now we get a stronger subsurface scattering effect very simply without having to re-render the scene. Or I can select my GI layer, press T, and decrease its opacity to something like 50. Now we have a darker indirect lighting. Let's set the opacity for the GI layer back to 100. The next thing I want to show you is how to use the light select render elements to control the lighting of the individual light sources in the scene. In the project panel, let's duplicate the basic composition and rename it to light select, and double click to open this new composition. Let me hide all the layers except for the lighting layer. Now we want to recreate this using the light select render element. We want to recreate the lighting render element using the light select render element. So hide the lighting layer as well, duplicate it, and rename it to light select sun. And in the extractor effect, choose V-Ray light select underscore sun and make the layer visible. And here we have the lighting contribution from only the sun. Duplicate the layer and rename it to light select underscore portal, and choose the light select portal render element from the extractor. Make sure the blending mode is set to screen, and here is the lighting contribution from the portal lights in the windows. And finally, duplicate the layer again, rename it to light select underscore candle, and choose the relative render element from the extractor. And there we have the lighting from the candles. Now I can have real-time individual control over my different light sources even after the render has finished. I can select the portal lights layer and decrease its opacity, for example, or set its opacity to 100, duplicate the layer, and this way make the light even stronger in the scene. For now, let me just delete the duplicate here. And now if I turn on the other layers, we are gonna have the same image as our final render, even though the light select passes that we exported have some specular information because their mode in the render elements tab in 3ds Max was set to normal, I think. I think the light select render elements also has a diffuse mode that won't include any specular information, but in this case we can manually turn off the specular layer even though it doesn't make any specific difference in the scene. As I was explaining different render elements, I mentioned that, for example, global illumination render element is formed by multiplying V-Ray raw global illumination render element with the V-Ray diffuse filter render element. Now let's practically do that. And V-Ray lighting is formed by multiplying V-Ray raw lighting and by V-Ray diffuse filter. So the same thing here. I'm going to explain it for global illumination, and you can do the rest on your own. Let's create a new composition based on our original EXR file and name this composition something like GI reconstruction. Again, apply the extractor effect to the layer here. Click in this empty space in the extractor effect and choose V-Ray raw global illumination. Also, let me rename the layer itself to raw GI. Now we need our V-Ray diffuse filter render element, so duplicate the layer, rename it to diffuse filter. In the extractor, choose V-Ray diffuse filter render element. And set its blending mode to multiply. Now we have reconstructed our global illumination render element. Now let's use this reconstructed GI render element instead of our original GI render element. So in the project panel, duplicate the basic composition and rename it to something like complex composition. I don't want to change the basic composition for now, and open up the complex composition. Now we can turn off our GI layer in this composition and instead use the GI reconstructed composition as the GI layer. Just make sure its blending mode is set to screen and preserve underlying transparency is enabled for the layer. Here we can do a lot. For example, we can tint our global illumination solution without affecting any diffuse color in the scene. So in the GI reconstruction composition, hide the diffuse filter layer for a moment and apply a curve color correction to the GI layer. Just go to the red channel and make the image a bit warmer. Now if I turn on and off the curve effect, you can see we get a warmer GI solution. And if I get back to the complex composition, you can see how this change made the overall image a lot warmer. To compare it quickly, let's take a snapshot. Disable the GI reconstruction and enable the original GI pass. And now if I click on the show snapshot, you can see how it made the scene warmer without affecting the other colors in the scene and tinting those colors basically. Now let's hide the GI layer and unhide the GI reconstructed or reconstruction composition as the GI layer. And in the GI reconstruction composition, disable the curves correction. Another thing I want to show you is how to use the multi-matte render elements to isolate a certain object in your image and adjust it the way you want without affecting other objects. In this case, let's change the color of the wall. We can go to our basic composition and isolate the wall and adjust its color. And I'm going to show you how to do that very simply, but I'm going to do it on a more fundamental level first. If I go to my complex composition, you can see that the color of the wall is coming from the lighting and the GI pass, and mainly the GI pass. We have reconstructed our GI render elements. Now we need to reconstruct the lighting pass as well, but I'm gonna leave that for you to save some time. The dominant color is coming from the GI pass, so let's take care of that first. Let's go to the GI reconstruction composition. We want to change the color of the wall, so the first thing we need to do is to isolate the wall, and we are going to do that using our first multi-matte render element. So let's bring in our original EXR file, rename it to mask for the wall maybe, apply extractor, and select multi-matte element 01. Now in the effects and preset panels, search for an effect called set channels, apply it to the layer, and in its controls we are only interested in the red channel, so let's turn off green and blue channels in the effect. Also make sure the red channel is also the source for the alpha channel in the set alpha to source dropdown. Great, now we have isolated the wall. We'll create a new adjustment layer from the layer menu and make sure to place it under the mask layer. Apply a hue and saturation effect to the adjustment layer. Right now, if I change the hue, it changes everything. But if I change the track matte for this layer to the alpha matte from the above layer, now it only affects the wall. But if I turn off the diffuse filter layer, you can see it also affects the raw GI layer as well. And we don't want that. We just want to change the color of the wall in the diffuse filter layer, right? In this case, the solution is very simple. Right now, the blending mode for the raw GI layer and diffuse filter layer is set to normal and multiply. However, because we are multiplying these two layers together and we don't have any other layer beneath them, we can simply change the blending mode for the raw GI layer to multiply as well. And the order of these two layers really doesn't matter in this case. It doesn't matter which one is above which. So I can set my raw GI layer on top of everything, and this way the adjustment layer only affects the diffuse filter layer, because adjustment layers only affect the layers that are beneath it. Now we can change the color of the wall the way we want. In this case, let's use, I don't know, maybe something like 322 degrees as the hue, a beautiful green color. There we have it. We have changed the color of our wall. Now if I go to my complex composition, you can see the wall has a new color, but we are still getting some of that original color from the lighting pass, and we need to adjust that too. And I'm gonna leave that to you. Simply reconstruct the lighting pass by multiplying the very raw lighting and very diffuse filter, isolate the wall and adjust its color the way we did it in the for the GI pass, and use the resulting comp instead of the lighting layer in the complex composition. Or we can simply select the adjustment layer and the mask layer, press Ctrl and C to copy them, get back to the basic composition, press Ctrl and V to paste those two layers, make sure the adjustment layer is below the mask layer. And now we have changed the color of the wall, and it works just nice and fine here. Let me just rename this adjustment layer to wall CC, which stands for color correction. The final thing I want to show you is how to use the Z depth render element to generate beautiful depth of field effects in After Effects. It is very simple. In this simple composition, let me first turn off the adjustment layer. We don't need it for now. Sometimes the extractor plugin has problems with the Z-depth path, so I'm gonna use the separate paths that we saved out. So in the project panel, open up the separate folder and bring in the Z-depth path. And here in the composition, we can see our Z-depth render element. Now we can go ahead and hide this layer as we only need to use it as the source for another layer. Add a new adjustment layer and let's name it depth of field or whatever you are comfortable with. In the effects and preset panel, I'm gonna use a plugin called depth of field from Frischluft, which is a commercial plugin well worth the money. If you don't have it, you can use the native lens blur effects, and it's doing a similar job, but this plugin is, in my experience, is doing much better job, and it really produces beautiful depth of field effects, and it gives you tons of controls to control the iris shapes and stuff like that, which makes it amazing. In this plugin, first you need to define the depth layer, which is our Z depths. There we go. Make sure to define this. Radius controls the amount of blur that you want. Let's set it to 10 for now. Just we can obviously see where is in focus and where is out of focus. Using select depth, you can define the focus distance of your camera simply by clicking on the object that you want to be in focus. In this case, let's select the books. Now the books and everything in the same image plane will be in focus. Basically everything that has the same distance from the camera as the books will be in focus, right? And now it's basically when you click here, the plugin is actually picking the shade from the Z depth path that we have defined as the depth of field layer. And this way, basically everything that has the same shade and is in the same image plane and has the same distance from the camera will be in focus. If I select this candle, they will be in focus, or if I select this frame here, the books, the candles, and the chair will go out of focus. I mean, we are using an 80mm lens, so we don't have much perspective and much depth, so but we still getting this beautiful depth of field effects. Okay, let's make sure the books are in focus for now. The depth of field plugin works really amazing, and there are so many other options in this plugin to adjust and get really good depth of field effects, but this is enough for now. For now, let me disable depth of field as well. And finally, let's duplicate the lighting layer and rename the new layer to background and put it beneath everything. And in the extractor, choose the background render element. And here is our background. Obviously, if the background appears a bit darker or a bit brighter, you can simply apply an exposure effect and decrease or increase its exposure to make it the way you want. We can turn on our depth of field layers as well, maybe. I mean, there are so many other things that we need to discuss in compositing and how to do it, but unfortunately, we can't make this lesson any longer. It's already very, very long, but hopefully you can continue by searching on the web and watching other tutorials and get your compositing going on. So in this lesson, we learned about render elements and how to composite them inside After Effects. In this lesson, we take a look at very quick settings. To access very quick settings dialog in the very toolbar, click on this icon, and now we have very quick settings window. Instead of having to go through all of those complex render settings, here you can control the overall quality of your render in a very simple and user-friendly interface. First of all, up here you have 4 presets. The first one from the left side is exterior preset, and if I select this preset, the render settings will be adjusted for architectural exterior visualizations. For example, if you come down here to this GI dropdown, you can see brute force, or BF, has been used as the primary and secondary GI solution. Next we have the interior preset, and as I do so, and as we need to calculate a lot more GI bounces to get acceptable result in an interior scene, irradiance map and light cache has been used as the primary and secondary GI engines. We have VFX preset for the scenes that you have some sort of VFX theme and you don't require GI, and that's why GI is off in this preset. We have the studio preset for product shots, obviously, and in this case GI is set to brute force and light cache. Using this button you can save out or load presets, and we discussed this earlier. We have these 3 simple sliders to control GI quality, shading quality, and anti-aliasing or image sampling quality without having to go through the settings and manually control all of those parameters. Right now we are using the studio setup preset and the GI quality is set to 0%. In this quality you can see brute force subdiv is set to 8 and light cache subdivision is set to 500. If I increase the quality, let's say to 50%, now brute force subdivs is set to 32 and light cache subdivs is set to 1500. And this results in a cleaner render, obviously, but with increased render time. But we didn't have to go through and manually control all of those stuff, right? Which is good. Using this drop down, you can select different GI combinations for primary and secondary engines. And if I click on this settings button, here it takes me to the render setup window and GI tab to adjust any other parameters that I want. We can control the shading quality by increasing and decreasing the shading rate value. And finally, we can control image sampling quality using this AA or anti-aliasing slider. For example, if I set the quality to 10%, 1 will be the minimum image sampling subdivisions and 2 will be the maximum subdivisions, and 0.05 will be the noise threshold. And obviously this is going to give us a very noisy render. And if I increase the quality to something like 90%, the minimum subdivision is 2, maximum is 22, and noise threshold is 0.002, and this results in a noise-free render, but with a very huge increase in render time. We can define bucket or progressive image sampling, or click on this settings button and go to the extended image sampling settings. And using this checkbox down here, you can enable or disable a very virtual frame buffer. And after you are done adjusting the render settings, you can click on this render button and render your scene. So if you want to use V-Ray but looking for a much simpler workflow, you can use V-Ray quick settings dialog, which is going to be very, very helpful. So in this lesson, we learned about V-Ray quick settings, and I will see you in the next lesson.